Welcome to the Deep Dive, your shortcut to being well-informed. Today we're really getting into how machines understand the visual world. And it's a lot more subtle than you might think. I mean, think about it. You see let's say, a baby goat in a field. You don't just think animal, right? Your brain instantly picks up all sorts of things. Its fur color, its size, maybe that it doesn't have horns yet, or just that it looks, young and healthy. These details, these attributes are just fundamental to how we see things. But getting machines to do that, that's the huge challenge in computer vision, especially in what they call an open vocabulary way, meaning recognizing things they haven't been specifically trained on, like knowing crimson if it only learned red.
Exactly. And that's really where the traditional ways of teaching attribute detection they hit a snag. The sheer amount of work needed to teach an AI every single possible attribute for every object, it's enormous. You need these huge manual annotation efforts. But the annotations themselves are often, sparse, not always consistent. They're incomplete because who lists every attribute? And they're definitely subjective. Take that goat example you mentioned, maybe from figure 1 in the paper. One person labels it brown, another says reddish brown. That kind of ambiguity, plus just the scale of it all, makes true open vocabulary detection incredibly hard and very expensive for the older systems.
Okay, so that sets the stage. Today, our mission is to explore this really fascinating breakthrough that tries to cut through all that complexity. It's called Compositional Caching, or ComCa. And we're going to unpack how ComCa manages open vocabulary attribute detection without any specific training for those attributes, which sounds, honestly, pretty radical, a truly innovative approach. So let's dig into those limitations first. If machines struggle with this nuance, what are the actual roadblocks? Why has it been so hard?
Well, traditionally, we've mostly relied on, let's call them predefined sets, fixed lists of attributes. It's kind of like giving the AI a dictionary with only red and blue in it. If it sees crimson or sky blue, it's just lost. It doesn't have the word or the concept.
Right, it's constrained.
Exactly. And that comes down to a few core problems. First, that annotation burden we mentioned. It's not just time-consuming and expensive. It's also, like we said, full of ambiguities. The goat example again, brown, reddish brown. Trying to label every nuance for every object just doesn't scale. It's a huge bottleneck. Second, you've got issues with scalability and adaptability. If your model only knows the attributes on its list, that's it. It can't easily recognize new ones or adapt to different tasks. If it only learned happy and sad, it's not going to understand pensive or elated. It lacks that flexibility.
So it's brittle, in a way.
Very much so. And third, even some of the newer open vocabulary approaches that do use training, they still struggle with something called generalization bias. What's really telling is when you look at the research, like in figure 4 they show this, their performance often drops significantly in cross-dataset experiments, meaning you test them on images different from their training data, and they just don't perform as well. They inherit biases from the data they saw.
Which points to needing a different way of thinking about it, right?
Absolutely. A fundamentally different approach that isn't tied down by those training biases and can generalize better.
So the bottom line is, these limitations mean AI might identify a car, but it misses the rusty blue vintage car stuck in mud level of detail.
Precisely. We're hitting a wall when it comes to genuine human-like understanding, and trying to bridge that gap with more and more labels is just becoming unsustainable for that really fine-grained perception we want.
Okay, so that's the challenge clearly laid out. Now, ComCa, how does it tackle this, especially being training free? That still sounds kind of like magic. How does it learn anything?
Well, it's not magic, but it is really innovative. ComCa flips the script. It's training free specifically for the attributes. It does this using a clever auxiliary cache. Think of it like building a dynamic memory or library. Instead of learning from scratch, it intelligently retrieves and combines existing knowledge.
An auxiliary cache, okay.
Yeah, and one of its first big innovations is making this cache scalable while understanding compositional nature of attributes. Because think about the scaling problem, just trying to store a few examples for every single possible attribute combination, like every shade of red for every type of object.
It would be astronomical. Impossible.
Exactly. Prohibitively expensive. So ComCa needed a smarter way. And this leads to its first really key insight, this idea of attribute-object compatibility. This is where it gets really clever. ComCa realizes that, not all attributes fit all objects equally well. Wet car makes sense. Wet dog makes sense. There are different kinds of wetness, but they work.
But wet idea doesn't really work.
Right. So ComCa estimates this compatibility. How well does an attribute like wet go with an object like car? It does this by combining two powerful information sources. First, it looks at database priors. It mines huge image text databases, like CC12M has, 12 million pairs, to see how often attributes and objects actually appear together in real-world descriptions.
So it learns from how people actually describe things.
Exactly. It taps into that real-world distribution. But then it also uses large language model reasoning. It queries powerful LLMs like GPT 3.5 Turbo, asking basically, how likely is this attribute-object pair? This adds a layer of common sense reasoning.
Ah, okay. So it's getting info from both real data and model reasoning.
Yes. And crucially, it multiplies these two scores. The research, the ablation studies in Table 4 and 12, showed this combination is much better than using either one alone. They provide complementary information.
So it's like building a really smart, curated library. It's not just dumping examples in. It's figuring out which examples are most relevant and sensible for a given object attribute query. It knows what belongs together.
That's a great way to put it. It understands that red car and red apple are both valid, but the implications and relevant visual examples might be quite different.
Okay, that's the Smart Cache Foundation. But you mentioned another key piece, soft labeling. What's that about?
Right, that's the second major innovative principle, and it's based on the simple truth. Every object inherently possesses multiple attributes. Think about that car again. It's not just large. It might also be blue, shiny, maybe metallic, four-wheeled. Objects are complex, right?
They're a bundle of characteristics.
Exactly. Now, the problem with the simple cache using hard labels is that an image you pulled because it showed a large car might only be labeled large in your cache. This completely ignores that it's also blue and shiny. And this can actually hurt predictions. If the input image is a small blue car, that cached large car example might wrongly contribute to predicting large and offer nothing for predicting blue.
Ah, I see. The hard label is too simplistic.
Yes. So the soft labeling solution fixes this. For each image in its cache, ComCa calculates these soft labels. It uses the underlying vision language model to compare the cached image's visual features against all the target attributes. So that large blue car image, it still gets a high score for large, sure, but it also gets a good score for blue and maybe for shiny, maybe metallic.
Okay, so one cached image can represent multiple attributes simultaneously.
Precisely. And this is really the crucial aha moment for understanding how it captures nuance. It lets a single cached image contribute evidence towards multiple attribute predictions. This much better reflects the real world, where things aren't just one thing. It helps capture the full picture, the whole visual story.
That makes a lot of sense. It's moving beyond single words.
Right. And there's also a normalization step in there, which is important to handle the modality gap, basically making sure the visual scores and the language scores are comparable so one doesn't overwhelm the other. The studies, Table 5, for example, confirm soft labeling consistently gives a significant performance boost.
So it sounds like ComCa isn't just seeing the keywords, it's understanding the whole context, the relationship between attributes within an image, painting a much richer picture. Okay, so we've got this very elegant design, training-free, smart caching soft labels. Does it actually work? How does it perform against other methods?
Oh, it definitely works, and the results are quite compelling. First off, it significantly outperforms the standard zero-shot methods and other cache-based approaches like Rossi ED or tip adapter. We're talking noticeable gains on benchmarks like OVED and VAW. For example, on OVED, it got something like a plus 10.6 map boost compared to a basic image-based cache baseline.
Endpoints is a big jump in this field.
It really is. It translates to a much more accurate understanding of those subtle attributes. But here's what's really fascinating, and maybe the most surprising part. Even though it's training free for attributes, ComCa is very competitive with recent training-based approaches. It even beats some models that were trained sometimes on huge data sets. That's a massive gain in efficiency, right? Getting similar or better performance without all that costly training and annotation.
Wow, so it sidesteps a lot of the heavy lifting, but still delivers.
Exactly. And another key strength is that it's model-agnostic. The research shows it works well on top of various different base vision language models, CLEPI, SIGLIP, ComCa, BLI-X VLM. It boosts the performance of all of them, as shown in Table 2.
So it's flexible. You can plug it into different systems.
Precisely. It shows the core idea is broadly applicable. But maybe the most profound advantage is its cross-dataset generalization. Remember we talked about training-based models degrading on new datasets. Figure 4 really highlights this. They inherit biases. ComCa, because it doesn't have that attribute-specific training phase, does not inherit these biases nearly as much. It maintains strong performance when faced with new, different kinds of data that shows real adaptability.
That seems incredibly important for real-world use.
It is. And qualitatively, you see it too. The examples in figures 3 and 9 show QMCA making more nuanced calls, avoiding contradictions like correctly getting a zebra's texture or a bear's color, or even seeing a phone is two-colored when others get it wrong.
So if it performs this well without the traditional training burden, what does this really mean for how we develop AI? It feels like it could change things quite a bit.
Well, just to quickly touch on the why it works so well, the ablation studies really back up the design. They confirm that combining the database priors and the LLM scores for the cache is crucial, much better than either alone or just random sampling, as shown in Table 9. And the soft labeling. That consistently gave a big boost across the board. Table 10 shows this clearly. It really validates the importance of capturing that compositional nature. Plus, it's pretty robust. Figure 5 shows it works well even if you vary the number of samples you cache for each attribute.
So the specific innovations, the smart cache construction and the soft labeling, they really are the key ingredients. It's solid engineering, not just luck.
Definitely, those design choices are critical.
Okay, so today we've taken a really deep dive into compositional caching, ComCa.
A genuinely innovative way to handle open vocabulary attribute detection. It's exciting stuff. Yeah, it really is. We've seen how it leans into the compositional nature of the world, how objects have multiple attributes. It uses web-scale data and LLMs to build that smart, scalable cache. And then that soft labeling scheme cleverly captures the richness within each image example. And the bottom line, state-of-the-art results, or close to it, without any specific attribute training. That makes it super adaptable and free from those tricky training biases.
And that training-free and model-agnostic aspect feels like the real game changer. You could imagine applying this much more easily to specialized areas, right? Like, say, analyzing aerial images for environmental science, or maybe medical scans, or specific industrial parts for quality control. Areas where getting massive labeled data sets for every possible attribute is just impractical.
Absolutely. The cost and time savings could be enormous, making sophisticated attribute understanding feasible in domains where it wasn't before.
So what does this all mean for you listening in?
Well, it brings up a really interesting question to think about. If a system like QMCA can achieve such impressive visual understanding without needing explicit training for every detail, relying instead on clever caching and compositional reasoning, what new frontiers could this unlock for AI, especially in fields where creating detailed training data is just too difficult, too expensive, or maybe even impossible? Where else could this kind of approach make a difference?